This is Mrs. Palmer-Quay with the fourth video for Module 12. In this video, I want to talk about Dalton's laws of partial pressures and vapor pressure of water. Pressure is one of the basic characteristics of all gases, and gas pressure results from the collisions between gas particles and the walls of the container. When you have a mixture of gases, every type of gas found in the container contributes to the pressure. They can't be present in the container without adding to the pressure. And so you see a direct relationship between pressure and moles of a gas. The Avogadro's law applies to mixtures as well as pure gas substances. This illustration down below shows that gas A is going to be colliding into the walls of the container at a certain pressure, and gas B also will be colliding into the walls of the container, so that when you put them together into a mixture, you're going to have two different types of gas particles, but they will still be colliding and contributing to the pressure. Dalton's law of partial pressures just states that the total pressure of a gas mixture is equal to the sum of all of the partial pressures contributed by each type of gas. It's just restating what seems very logical. If you mix together a sample of hydrogen gas that had a pressure of 1 atmosphere with a sample of nitrogen gas that had a pressure of 1 atmosphere and a sample of oxygen gas with a pressure of 1 atmosphere, the mixture with all three gases present would have a pressure of 3 atmospheres. So you are adding together the pressures contributed by each individual gas to make the total pressure of the mixture. In order to calculate the partial pressures, the fraction of pressure that's provided by any one gas in a mixture, we use the mole fraction. And this is the ratio, it's a decimal of result when you take the moles of the particular substance you're examining and compare that to the total number of moles present in the mixture. So for example, if in this box we have 24 moles of gas particles, then we can see for molecule B we have 6 moles present. So if you have 6 moles of B out of the total of 24 moles in the mixture, then the amount of the ratio for B would be, 1 to 4 or 0.25. So here's our mole fraction of B. The mole fraction of B is 0.25, and we can use that then to determine if we know the total pressure in the box. Well, 25%, basically 1/4 of the pressure, was going to be provided by the particles of gas B. So to give you an example of the type of problems you'll have to solve, this says a flask contains 1.24 moles of hydrogen gas and 2.91 moles of oxygen gas. If the total pressure is 104 kilopascals, what's the partial pressure of each gas? So the first question you want to ask is what's the total moles? Because we have hydrogen gas and oxygen gas, and so we have to add these two things together. We have to add 1.24 and 2.91, and that will tell us that we have 4.15 total moles. We need that value in order to figure out the mole fraction. Then for hydrogen, what do we have? We've got 1.24 moles of hydrogen out of 4.15 moles. And if you do the math, you'll find that that's 0.299 is the mole fraction for hydrogen. For oxygen, actually this is hydrogen as diatomic. For oxygen gas, we have 2.91 moles, and again over the total moles is 4.15, and then that gives us a mole fraction of 0.701. Once you have the mole fractions, the next step is to figure out the partial pressures, and you do that by taking your mole fractions and multiplying it by the total pressures. So for hydrogen we have a mole fraction of 0.299. We multiply that by our total pressure of 104 kilopascals. And if you do the math, you find that you determine that there are 31.1 kilopascals out of that 104. That's how much pressure is being provided by the hydrogen. That's the partial pressure for hydrogen. For oxygen, we do the same thing. We take its mole fraction, 0.701, and multiply that by the total pressure of 104 kilopascals. And again, if you go ahead and do the math, you'll find that there is 72.9 kilopascals of pressure provided by the oxygen. So this is a pretty straightforward process. You figure out the mole fraction by putting the number of moles of whatever gas you're considering over the total moles, and then you just take that number, that ratio, that fraction, and multiply it by your total to get your partial pressures. Although we won't have an opportunity to do this in our lab situation, many of the gases that can be produced by chemical reaction are then collected in a method called water displacement. So you can see down here we're having a reaction between an acid and a metal. That's one of the characteristics of acids, that they react with certain metals to produce hydrogen gas. And so this gas then is bubbling up and it's being collected down this tube and going underwater and into this, sometimes a graduated cylinder or some type of container that was full all the way to the top of water, but as the gas fills it up, the gas is collected, the water is displaced, it's pushed out. But because there is this surface of water here, we do have some evaporation occurring. Little water molecules are moving from the water surface into this little atmosphere inside the container. And so any gas that's collected by water displacement is mixed with a small amount of water vapor. If you want to determine how much gas you've collected, you have to consider the water vapor. You can't ignore it. We have tables that tell you what the vapor pressure of water is at distinct temperatures. The tables sometimes their tables are put in whatever pressure unit you need. You can find them for all. This particular pressure unit is either millimeters of mercury or torrs, since they both have 760 being equivalent to 1 atmosphere. So that it tells you that if you're collecting a gas over, let's do it at standard 20 degrees at our laboratory conditions, if you are collecting a gas over water, then 17.5 millimeters of mercury or torrs, that is the pressure of water vapor, the partial pressure of water vapor in your gas. Your gas that you've collected is a mixture, and 17.5 millimeters of mercury is being provided by vapor pressure. Notice over here at 100 degrees Celsius, which of course is the boiling point, the vapor pressure equals 1 atmosphere. 760 millimeters of mercury, or 760 torrs, is equal to 1 atmosphere. That when the vapor pressure matches the external atmosphere, that is when you have boiling. When the gas that is forming inside the liquid as the particles are heating up and changing state from liquid to gas, when those gas bubbles can actually leave as boiling, the vapor pressure is equal to the atmospheric pressure. Here's an example of the type of calculation you might be asked to do using water vapor. It asks, a certain experiment generates 2.58 liters of hydrogen gas, which is collected over water. The temperature is 20 degrees Celsius and the atmospheric pressure is 739.7 millimeters of mercury. What is the partial pressure of the hydrogen gas, and what would be the volume of the dry hydrogen at STP? There are 2 parts to this question. First, they're asking you to calculate the partial pressure of the hydrogen gas. And then once you know that partial pressure, then how would it change? How would this dry hydrogen, when the water's been taken out, what would the volume do at STP? So the first thing you need to do is consider what the partial pressure of hydrogen gas is. You do that by taking your total pressure of 739.7 millimeters of mercury, and you refer to a table like the one on the previous slide, which will tell you that there's 17.5 millimeters of mercury of water vapor present when you are at 20 degrees Celsius. So you use that reference to get your value for your vapor pressure. And so if you do this math, you find that you have collected, or the partial pressure of the hydrogen gas is 722.2 millimeters of mercury. So out of the total of 739, 722 was because of the hydrogen gas in there. So then we have a pressure, we know a temperature, and we have a volume. So to go calculate a new volume, we need to use the right gas law. This one we don't need the ideal gas law because we're comparing an old situation to a new situation. So we need the combined gas law, which tells us that P1 V1 over T1, our first experimental conditions, will equal that gas in P2 V2 over T2, our second situation. So this is the experimental conditions we've heard about, and then our second condition will be at STP. STP, standard temperature and pressure, remember, is 0 degrees Celsius and 1 atmosphere, or to put it in terms that we'll need for this problem, it is 273 Kelvin and 760 millimeters of mercury. Since we're being asked to calculate a new volume, we do need to rearrange this problem so that we have our volume number 2 is going to equal P1 V1 T2, all divided by T1 P2. And then once you have this set up, it's just plugging in the numbers and doing the calculation. So our pressure 1, we figured that out. Our partial pressure is 722.2 millimeters of mercury. Our current volume, the amount of volume of hydrogen that was collected, was 258 liters. The new temperature, I see I didn't put a 2, this is supposed to be a 2 here, T2, our new temperature is going to be 273 Kelvin at standard temperature and pressure. That's 0 degrees Celsius or 273 Kelvin. Our original temperature is 20 degrees higher than that, so it's 293 Kelvin. And then our new pressure would again be at STP. It tells us that that's at 1 atmosphere or 760 millimeters of mercury. So once you have all of your units and your values into this problem, it's just a simple case of doing the math, and you do all of the number crunching, you find out you will have collected at STP your 2.54 liters would only be 2.28 liters, which is not really a surprise because you're going from 20 degrees Celsius down to 0 degrees Celsius, and as substances cool, they do tend to pull together a little bit. If they cool enough, they turn into a solid. Though, of course, with something like hydrogen gas, you'd have to get really cold to get it to be a solid. But anyway, this gives you an example of how you might be asked to work with water vapor and also reminds you about that combined gas law. This finishes up what I wanted to say for this 4th video for Module 12.